Thank you. Hello, everyone. Welcome to the webinar on alternatives to the traditional p-value. I am Esra Kurum from University of California, Riverside. And since the publication of the ASA statement on p-values in 2016, many statisticians have been thinking and working on the alternative methods to the p-value. And these works have led to the recent publication of the special issue of the American Statistician. And today we are very fortunate to have three distinguished speakers who will provide us a synopsis of these alternative ideas. And here is our schedule for the next 2 hours. After my introductory remarks, Dr. Nicole Lazar from University of Georgia will provide us a recent history of this topic, followed by Dr. Denjeski from University of California, Riverside, who will give us a technical overview of some of the alternative methods. And then our third speaker is Dr. Jessica Utz from University of California, Irvine, who will talk about, in the light of these alternative ideas, how we might teach and influence our interdisciplinary collaborators. After each speaker, we will have some time for questions. And at the end, we will also have some time for further discussion and Q&A from the audience and the speakers. Unfortunately, our fourth speaker, Dr. Nell Sedransk, will not be able to join us today. And here is some information about today's logistics. Glenn Johnson and James Rosenberger, the director of the NISS, are the hosts for our session. All our attendees are Viva-only participants, but we also encourage all our attendees to submit questions. Zoom attendees can use the Q&A feature of the Zoom window to ask questions. To do this, just click on the Q&A icon at the bottom of the Zoom window, type in your question, and then click enter. For the attendees who are viewing through the YouTube, they can send their questions as an email to communications@niss.org. We will be monitoring this email account. And finally, some information about the Zoom settings. If you want to minimize the videos of the other speakers when a speaker is sharing his or her screen, you can click on the dash button that appears on top of the videos of all our speakers. And I would like to introduce our first speaker, Dr. Nicole Lazar, who is professor of statistics at the University of Georgia. She received her undergraduate degree. She received her undergraduate degree in psychology and statistics from Tel Aviv University, master's in statistics from Stanford University, and PhD in statistics from the University of Chicago. She was on the faculty of Carnegie Mellon University until 2004, moving in that year to the University of Georgia. Professor Lazar is an elected member of the International Statistical Institute and a fellow of the American Statistical Association, as well as past editor-in-chief of the American Statistician. She's currently also serving as president of the Caucus for Women in Statistics. Today, Nicole will talk about the recent history of this topic and the motivation behind the American Statistical Associations and the American statisticians' involvement with this topic. Nicole?
Okay.
Nicole?
Yeah, sorry, I was muted. Can you hear me now?
Yes, we can.
Okay, thank you. All right, so first I'd like to thank Ezra for the introduction, Dan for organizing this, and NISS for hosting this, and all of you for being here. This is going to be a little bit of a personal history as well as a more general history. So parts of it I was involved in and parts of it I wasn't, and so that's why some of it is a little bit more personal than others. And I'm going to be talking about the recent history of a statement, a special issue, and a controversy. So this is not by any means a new topic, of course, as we all know, but I'm going to restrict my comments mostly to the last 10 or 15 years or so. And I'm dating the current conversation to some of these early signs. So in particular, I think a first warning shot was the 2005 paper by NISS, Why Most Published Research Findings Are False. And in this paper, he pointed out many issues with the medical literature in particular, and why, in his opinion, again, as the title says, very provocatively, most published research findings are false. This started a trend of papers and discussion that were pointing out misuses and abuses, not only of statistical methodology, but a fair bit of statistical methodology in the middle of it, including hypothesis testing, uses and abuses of p-values and misuses of p-values, and misuses of multiple testing problems, and other things that we'll see later on as well. So there was this conversation sort of bubbling along in the background, and in my own area of application, which is functional neuroimaging, there was some of this going on as well. And there were various famous or infamous, depending on how you want to think about them, papers that pointed out problems with how people were doing statistics and issues of replicability and issues of inference. 2014, the journal Basic and Applied Social Psychology published an editorial from the editor-in-chief saying that they would no longer require null hypothesis significance testing procedures, or NHSTP, or more broadly, inferential statistics. They didn't go so far as to ban anything at that point, but in 2014, they said they were no longer going to require it. In 2015, Trafimo and Marks, again in an editorial in Basic and Applied Social Psychology, strengthened this position, and they banned the use of p-values, as well as, and I quote from their editorial, all vestiges of the NHSTP, p-values, t-values, f-values, statements about significant differences or lack thereof, and so on. So this was a pretty bold statement that caught a lot of attention for those of us who were sort of listening in on this conversation. And so that was really, I think, what got a lot of this going in a more serious way. At the same time, there was this perception of some sort of crisis of replicability or reproducibility in science. Whether it's a replicability crisis or a reproducibility crisis depends a little bit on who you talk to and a little bit on how you define these things. But this was popping up in various areas of science. I've already mentioned neuroscience, but also in social psychology very strongly, in cancer trials and so on. And these problems were starting to gain more attention, including actually in the popular press. So this wasn't just conversations among scientists. There was an article in the New Yorker, even in 2010, called "The Truth Wears Off." And it was, I remember reading it at the time and thinking that it was pretty interesting that this sort of arcane notion in science and statistics was getting reported in the New Yorker, and so reaching a broad audience. And the gist of that article was that studies don't replicate. So you find this great, exciting result in, say, social psychology, and then someone else tries to come along and study it again, and the effect isn't as big as it was the first time. So what's going on? And if you keep studying it, it seems like it gets smaller over time. So that seems a little bit counterintuitive. And you know, what the gist of it? Where's that coming from? This wasn't a technical discussion by any means, but it shows that people are interested more generally. Around the same time as well, the Open Science Framework Reproducibility Project was taking off. In 2011, they published results in psychology that found low levels of reproducibility in published research. Ironically, that the same result is also not totally reproducible. So there's lots of interesting circles within circles here. And they've got now a project ongoing still in cancer biology. So people started to wonder, is there really a crisis in science? And if so, what is the role of statistics? And specifically the use of thresholds, such as p less than 0.05 for publication. And this was part of the picture, again, sort of based on where I was looking from the side at that point. And there was a lot of discussion about what you might call questionable research practices, such as p-hacking, where you slice and dice your data till you find your significant results, and then you publish those and forget about everything else. researcher degrees of freedom, where you can make all sorts of different choices, again, about what you're going to do, how are you going to analyze your data, how are you going to look at your data, but the only thing that you report are the significant results. And there were many signs of abuse of statistical methods starting to appear in the literature. So against this background, in 2015, 2016, the American Statistical Association convened a committee of experts to discuss these issues, the use, misuse, and abuse of statistics. And the statement on the p-values was the result of that. I was not actually on that committee. The first I heard of it was when I got an email from the ASA executive director saying that he would like to talk to me about something, but he couldn't do it over email, and could we have a phone conversation? So I said, sure. You know, ASA executive director asks for a conversation with you, so you say yes. And the conversation was around this statement, and he wanted to know if the American statistician would publish the statement on p-values. So my first question was, how do I make this into a real American statistician paper? I didn't want the journal to be used just as a platform for a statement. I took my responsibility as editor of the journal, to our readers very seriously. So I told Ron I needed a little bit of time to think about it. I didn't immediately say, oh yes, we will definitely publish this. I said I needed to think about this, and I needed to think about how to make it a real paper for us and not just a policy statement. So my answer that I came up for that question was to invite discussion. So Ron and I wrote an introduction to the statement, and we invited all of the participants in the original committee to write a discussion of the statement, because it was evident, and in my discussions with Ron, and evident actually if you read the statement itself, that not everybody agreed with everything that was in the final statement. And so we thought it would be interesting, and I thought especially for the readers of TAS, it would be interesting if we had all of those viewpoints represented. So not everybody agreed to write a discussion, but a fair number of them did. And so at the end of the day, many of the members of the committee contributed pieces, and we published this all as an online discussion. So we had our introduction to the statement, and the statement were published in the print version, and then the online discussion were all the comments from the people on the committee. And this brought, I think, a great awareness to the community and to me. I mean, I've really changed my thinking over the last few years as well, to these general issues: the use and abuse of p-values, the replicability crisis, the reproducibility crisis, however you want to think about it. So it's not that there was nothing going on prior to 2016, but I think that the publication of the statement definitely threw this into a much stronger relief. And for the first, we were coming out and saying something as a statistics field about where we need to go next. The next big step, and again, I wasn't really involved in this one directly either, the Symposium on Statistical Inference in 2017 in the fall. So the aim of the SSI was to continue the conversation that was started by the statement. There was a lot of interest obviously generated both within the statistics community and more broadly in the scientific community. The statement sort of emphasized things that we shouldn't do and how we shouldn't think about p-values. But now you need to move forward. You have to think about what we should be doing. So the symposium was to try to continue the conversation and generate ideas for moving forward. So it brought together statisticians and researchers from a wide range of disciplines with a wide range of perspectives. And really the question was, is there a problem with how statistical inference is commonly conducted? Not everybody agrees that there is a problem. If there is a problem, how serious is the problem? And if we agree that it's a problem, and we agree that it's a serious problem, what are some of the solutions? And so the symposium really was meant to provide the impetus for that next step. So not just saying, okay, yeah, we think there's an issue, but also, all right, so now what do we do about it? The symposium, speakers in the symposium gave many different ideas for how to move forward. And I'm going to include just a few of them here. We have things like lowering the standard p-value threshold for declaring statistical significance. So there's a suggestion out there that 0.05 is too easy of a threshold, so let's lower it to 0.005 and get rid of some of those false claims that can sneak into the literature that way. Another suggestion that's out there is to pick your alpha level, your significance level that you're going to work with on a case-by-case basis and justify it in light of sample size, in light of effect sizes, in light of what the literature tells you about what effect sizes should look like, and so on. Bayesian approaches are always popular, and they came up here as well. Alternative configurations of p-values, and so on and so on and so on. So many different types of suggestions on what we can do to move away from the traditional ways of doing things. Following the symposium, Ron had the idea, floated the idea to me and to Dan. I was no longer at that point editor. Dan Jeske had taken over as editor of the American Statistician. We floated this idea to put together a special issue of the American Statistician to build on the momentum from the symposium. So ASA worked with TAS to put together this special issue, which we've called Statistical Inference in the 21st Century, a World Beyond P less than 0.05. And I was one of 3 co-editors of that issue, along with Ron and Alan Sherm. We did this as a combination. Again, we thought very carefully about how we wanted to do this. We wanted to get participants from the symposium to contribute, but we also wanted the community more broadly to be able to participate in this and not have it be a sort of a members only by invitation type of thing. And so we decided on a combination. We had invited papers from the participants in the symposium, which went through rigorous peer review. And we also put out a general call to the community for papers. And we got a lot of submissions, and we read through them all and sent them to associate editors, and who sent them on to referees. So went through the whole usual process. The deal that we struck with the publisher was that the special issue should be open access. It's online only. It's freely available forever to everyone. We didn't want it to be behind paywalls. We didn't want it to be hard to access, because this is a conversation that we felt was really important for everyone to have and everyone to have access to. So that's the format. Anybody can get it, can read any of the papers whenever they want. The final issue has 43 papers. Dan will be talking about some of those in his presentation. And there are suggestions on how to move forward in many different areas, in education, in publication practices, and obviously in statistical inference more generally. So that's where the special issue is. So just to give you a little bit of a snapshot in time. So as of last week, May 15, 2019, the ASA statement on p-values had 315,539 views. As of that same day, the lead editorial to the special issue that Ron, Alan, and I wrote had 83,202 views. I looked this morning, just before this webinar, and it's close to 86,000 now. So in a week, it's gained another 3,000 views. Much conversation is obviously taking place in the pages of journals already, even before this, at conferences, again, already, even before this, among statisticians, between statisticians and scientists, between statisticians and science writers. How do we get to this post P less than 0.05 world, and do we want to? So that's the controversy that I alluded to in the title of my presentation here today. Not everyone, excuse me, not everyone is on board with this. I have to say, I've actually been really heartened by the response that I've gotten personally from scientists and science writers, that they understand, they've been feeling themselves that there's an issue and that they want to do things differently. And so those conversations, excuse me, are starting to happen. I've received emails and calls from science writers and from scientists on my campus and elsewhere. It's like, okay, so what do we do? How do we change this? And in fact, I was talking to someone just a couple days ago, and he said, I just wrote a paper in my field, which was some type of paleobiology, I think he said he was in. And he published something about statistical inference and how in the field of paleobiology, they have to make some changes in how they do inference. And then he said, and then a month later or 2 months later, this great special issue came out. So it's not that we're pushing an agenda that the time is not ripe for. So I would say stay tuned for future developments. I think we're really at a point in time now where there could be some positive changes. What those will look like, I don't know. We'll all have to wait and see. But people are, I think, ready for the conversation and open to the conversation, maybe in ways that they weren't before as much because of all of this other sense of crisis or of something sort of maybe broken in science and in statistics that we can now all collectively fix together. So I think that's the last of my slides, and I probably ended a bit early. So there's, I think, some time for questions as well.
Thank you, Nicole, for all the information on the history of this topic and how we started to actually have conversation on this issue and look for alternatives. One question is, what do you think could be the disadvantages of banning the use of p-values? As you mentioned, some journals stopped requiring any inferential statistical procedures. What could be the disadvantages or dangers of this approach?
Huh. So, we're not, at least in our editorial, we're not suggesting to ban the use of p-values. We're suggesting to use p-values, but on a continuum from, 0 to 1 as probabilities, and to recognize the fact that they're uncertain themselves, they're random variables themselves. So I think we need to make that distinction between banning the use of p-values and banning or discouraging the use of the phrase statistically significant and that bright line threshold. That's the thing that I think is more important to focus on. Anytime you put down a threshold, whether on purpose or not, people are going to try to find ways to get to that threshold. So I would suggest instead that we report p-values or some other measure, as well as effect sizes, measures of uncertainty, and recognize more clearly what the p-value is and isn't giving us. I don't know if that answers the question, but that's the best.
It does. So I think, I think it gives us the message that there could be disadvantages of completely banning the use of p-values as well.
Yeah,
exactly. One other question is, you mentioned early in your talk that some papers pointed out abuses and misuse of p-values. What do you think have led to this misuse and abuse, or how did this started so that we can avoid maybe these in the future when we start using alternative methods?
Yeah. That's I get asked that question a lot. So I think I need to go back to my history books and sort of figure some of this out. I mean, I think it's a combination of things, and I don't want to point fingers because I think this is just the way that the field has developed. I think part of it has to do with incentives. So how does a paper in a scientific field get published, right? And so that's why I'm really happy that there's some papers in the special issue that talk about changing publication practices, because scientists can try and change and statisticians can say, oh, we need to change, but there needs to be also that buy-in from funding agencies and from journals.
Right.
So that's part of it, I think. You have that incentive that you need to get to that magic 0.05 threshold in order to get your paper published, for anyone to even pay attention to what you're saying. So that's clearly a driver of a lot of this. I think if we can move away from that thinking, then maybe there's a hope to not fall into the same trap again. And also there's this conflation of significant, because that's a word that we use in our day-to-day life. It has a particular meaning, but in statistics it has a different meaning. But it's now all sort of munged up with each other, and I think again it's just sort of, as a term, it's become more or less useful than useful at this point in time. And so maybe we need to find some other way of talking about things.
Right. I think that's great advice, and just something that we need to think about for the future, how we can avoid these.
And it's not easy. I mean, if it were easy, we probably would have done this 50 years ago or 70 years ago, or whenever people first started talking about this.
That's true. It's difficult to change habits.
Yeah. Indeed.
Yeah. And I would like to now turn to our second speaker. Thank you, Nicole, so much for your talk. And our second speaker is Dr. Dan Jaski, who is professor in the Department of Statistics at the University of California, Riverside, where he served as the department chair during 2008 and 2015. He's an elected fellow of the ASA and served on the board of directors during 2014 and 2016. He is the vice president of membership for the International Society of Business and Industrial Statistics. He was an associate editor for the American Statistician for 8 years before becoming editor-in-chief in 2018. He is an associate editor for Applied Stochastic Models in Business and Industry and a member of the Program Affiliates Committee of the NISS. His research interests include classification and prediction methodologies, longitudinal data modeling, statistical process control methodologies, biostatistics applications, and reliability modeling. And with that, I'll now turn the mic over to Dan, who will give us a technical overview on alternative methods to traditional p-values. Dan?
Thank you very much, Ezra, and good morning to everyone from Riverside, California. I also wanted to thank Nicole for her introduction to this topic and for providing us with some perspective on the history, the origins, the controversies associated with this topic. And it's very important, of course, to understand all of that, to have perspective on what the future holds for this topic. And what I've gathered in my own reading is that it's easy to understand the weaknesses and the pitfalls associated with p-values, but sometimes the conversation is a little short on the alternatives that one could use to a p-value. And certainly it seems extreme to ban p-values and just present the data as descriptive statistics and to not use inferential procedures at all doesn't seem like that's anything we would want to do as statisticians. So it's refreshing to see in the special issue alternatives that are methods that we could implement. And some of them that I'm going to talk about today are not very much more difficult to implement than what we're used to doing with p-values already. So to me, the excitement about the special issue is justified in the sense that it really gives some more tools for us. And so I wanted to kind of emphasize and highlight some of the options now that we have. I was reminded of this commercial in 1984 about Wendy's hamburgers. And some of us will remember this, I'm sure, because the big question in this commercial is, where's the beef? And the lady on the right became quite famous for asking that question. And then it was repeated in many different contexts. And I think it's fair that it could be asked about p-value alternatives. What are we really supposed to do if we're not going to continue to use p-values? And so the answer to this question is scattered about in the special issue of TAS that came out in March and was alluded to in Nicole's overview. This special issue has 43 papers grouped into these 5 categories. And I'm mostly excited about well, I mean, they're all very good papers, but I don't have time to talk about all of them. I have a longer version of this kind of discussion where I talk about 17 of the papers. Today, I'm going to just narrow my focus to 7. And there are those are the ones that mostly fall into the categories 3 and 4 that you see that are kind of supplementing p-values. And then other ones that talk about holistic approaches. I love that word holistic. I even like saying the word holistic, but it's very appropriate in the context of statistical methods for analyzing data, because I believe you get more out of the data when you try to look at it more broadly than just perhaps a narrowly confined perspective, such as the routine p-value. So some of these papers are really good in the sense of sort of pushing us to look more broadly at what we're doing in data analysis. So, and I'll mention a couple of those. So I did want to point out too that there's a lot of literature behind these papers. So they aren't all presenting all brand new ideas. Some of them are highlighting and adding emphasis to previous work published elsewhere, because as we know, there's quite a long history on this topic. So sometimes bringing some of that history into the present is an important goal of these papers, and then adding something new to it as well. So I have these aims here that I do want to get a little bit under the hood with some of these methods, because they're very accessible. What I'm talking about here today, and most of what's in the journal, is very accessible from the standpoint of not only using, but teaching as well. It would not be very difficult to bring some of these new ideas into your classroom. And then I hope also that what I say here about the 7 papers I'm going to discuss makes you curious enough, if you haven't already. Apparently a lot of people have looked at the special issue, but if you haven't already, I hope that I might make you think about doing that. And finally, part of the holistic approach to this topic is really to bring together both Bayesian and frequentist thinking. So some of our alternatives aren't wedging us into one type of approach, but encouraging us to perhaps use both of these approaches in what we do. And I have some good examples of that as well. One last thing before we start. There was a very nice paper in the special issue that catches everybody up on the long history of p-values. And it isn't one I'm going to delve into today, because it's not so much about alternatives, but it's about history and what are the origins, the controversies, and who are the major characters over the decades of discussion on this topic. And I just wanted to mention this, as I think it might be one of the initial papers in the special issue. It's really good reading, especially for the students out there that want to kind of get caught up on where we've been to better understand where we're going. This is a highly recommended paper. So getting to it now, the first paper I wanted to mention has this title, Abandoned Statistical Significance. That even the word ban is part of abandon. So that almost sounds like we're supposed to do away with statistical significance, but really it's more, I think, the term statistically significant that is being referred to. It was mentioned by Nicole that this threshold idea can be a problem. And one of the things they wanted to emphasize in this paper is to not just say p is less than 0.05 or less than 0.01, but actually give the p-value so that people can understand more than just this bright line kind of you're below or you're above. The thing too is that they emphasize in this paper that one needs to be cognizant of the fact that small p-values are based on a lot of things, such as a model and assumptions associated with that model. So small p-values can exist not only because the hypothesis is in some doubt, but also because there could be inadequate assumptions behind it. And then they discuss also in this paper about sharp null hypotheses being poorly suited. And I'm going to talk more about that in some upcoming slides, because I think that's a very important aspect to this discussion, that testing whether a parameter is equal to a particular value is probably not the most important thing to be doing. And it has problems when it comes to rejecting hypotheses for effects that might not really have practical importance. So some of the slides upcoming will kind of delve into that a bit more. So this is an interesting paper, and I wanted to put in a little plug for an upcoming session at JSM. We do have a special TAS session on Monday, and it's at 10:35 in the morning. And this paper I just mentioned is one of the papers in that session. And these papers were kind of like really fun papers published in TAS in 2018. So I hope you might be able to make that session, and you can hear more about the abandoned statistical significance paper that I just mentioned. And And while I'm here, just many thanks to the 3 sections of ASA that put in their votes to have this special TAS session at JSM. Okay, so now let's get into more of the technical aspects, and we'll sort of gradually ramp up in terms of some of the mathematics, really. But as I said before, it's accessible mathematics in these papers. I think you're going to like them. This first paper introduces a new term, S values. Well, we have P values. Why not S values? And this is really a simple concept once you see it, right? Some of the best things we do, you say, I wish I could have thought of that. And that seems simple and it makes a lot of sense. So the idea here is you have an event E and it has some probability P, which you could represent as 1/2 to the power S. And then what you're doing is you're sort of translating the probability of that event as equivalent to what you would get if you had a fair coin and you tossed it S consecutive times and got heads each time. And so obviously S is minus log 2 of P. And so S, what you're trying to do is add context to the P value so that you can talk about it with your colleagues from other disciplines about how unusual is that event E. You know, if it has probability P, is it really that unusual? Well, they might not have the right reference to think about it, but everybody knows about tossing coins, and everybody has some intuition about what's the likelihood of getting S tosses of a fair coin landing heads every time. And that's what you're doing. So instead of reporting P, you can, here's an example. You can say if P is like our friend, 0.05, right? Then S is 4.3. So any event that has probability 0.05, such as a p-value, you know, evidence against the null is 0.05, that's really no different than doubting that the coin is fair because you got 4 tosses in a row that came up heads. And if we think about 4 tosses of a fair coin coming up heads, I don't know, to me, it doesn't seem like that's that surprising that could happen. And that's one of the arguments for 0.05 as a threshold of evidence, perhaps not being low enough. And Nicole mentioned that there's some discussion, and I'll show more of that soon, that maybe we should lower it to 0.005. And if you calculate the S value for that, it's 7.6, so let's say 8. Well, now, I don't think I would think that a fair coin could be tossed 8 times and get heads all the time. That seems a bit unusual. I'd start to maybe doubt that coin was fair to get 8 heads in a row. So this simple idea just helps, I think, you know, our collaborators, our interdisciplinary collaborators, understand more what a small p-value really amounts to. Is it really as small as it sounds? So coming again to this potential transition from 0.05 to 0.005. This paper is talking about that, and I'm going to delve into that a little bit here. But one of the things they wanted to say first is that if you wanted to do something in this regard, you could say that anything between 0.005 and 0.05 could be called suggestive rather than significant. And reserve that word significant for those p-values that are smaller than 0.005. So where does this kind of thinking come from? Let's see if we can reveal how this might have some substance to it instead of just an arbitrary, let's divide it by 10. It's not really that. There is some substance to this. And I wanted to show at least one of the motivating arguments. So consider this hypothesis test of a parameter equaling a certain value versus not. And what they want to do is recommend that you can go ahead and give the p-value, but you know, we all recognize that a p-value is kind of, it's the probability of some event involving the data given h0, right? And a lot of the researchers are more interested in the probability of h0 given the data, right? That's really, and that's really one of the biggest sources of confusion about what is a p-value and what isn't. So what they want to suggest in this paper is that you can supplement your p-value with a bound on what most researchers probably really want to know, which is the probability of H0 given the data. You can just think of X as the data here. I'm going to show this equation on the next slide because, again, it's simple mathematics, very accessible, and it's just good to know. Like, really, this is amazing. This is one of the most amazing results, I think, in the whole journal, as far as being so easy to use. Because look what it says. It says that we can bound the probability of H0 given X. Let's just move over to the bound. With this calculation, we already have our p-value, which could come from any kind of complex statistical model or data analysis you can imagine. You get this p-value, right? And you just plug it into this formula. And you do have to choose one thing, which is pi 0, the prior probability that you think this parameter is equal to the targeted value. And to make it concrete, you could think of maybe testing a slope in a regression model is equal to 0 or not, right? So you do have to come up with a prior probability for that. But that's not the same as coming up with a whole distribution for the prior on a parameter, right? That could be almost anything. This is just a discrete probability that this null hypothesis is true. And then if you can compute a p-value maybe from a least squares fit or something, you pop it into this formula and you get what probably most people want, which is the posterior probability that the parameter is 0 now, given that the data has been collected. And just as an example, let's say that we're kind of neutral about whether we think this null hypothesis is true. So we choose pi 0 to be 0.5. Here, for all these p-values, this table is showing what this bound actually computes to be. And if we had our traditional sort of 0.05 level of significance, it calculates to be 0.29. Isn't that surprising? Because that means that there's still, like, at least, because this is a lower bound, right? At least a 30% chance that the null is true with a p-value of 0.05. So that, again, is more of the accumulation of evidence that the 0.05 threshold isn't really that stringent. And that's when people start looking at other smaller values, and here is our alternative 0.005. Then you put that in there and you get something a little bit smaller, more like what we generally think of as our alpha level, because 0.067 is kind of close to 0.05. But the message here is that it's quite important to not just give a p-value, but you can supplement it. Remember the two words supplement and holistic for categories 3 and 4 of the papers. This is like a supplement paper, because the idea is to just also report this lower bound on the probability of the null, which is the kind of probability that researchers are often wanting to know and are confusing with the p-value. So I don't know, I hope that this is okay, but I wanted to just take a minute or two to show where this formula comes from, because as I said, think about teaching your students. How would you propose to introduce this into your class? It's very easy, really. Again, once you know how to do it, as these authors have now shown us. So we have this hypothesis, and there's a marginal density for X, which is a weighted average of the density of X given theta 0. And then here is where there looks like you're going to have to choose this G, which is the prior on theta. But the beautiful thing about this argument is we're going to get rid of G, and we're not going to need to actually choose it at all. So we find so this is really just the law of total probability here. And then this is Bayes' rule to calculate the probability of H0 given the data. That's just Bayes' rule, simple stuff. And this is just algebra to get this expression for it. And we introduce this Bayes factor, and the Bayes factor is defined here. It's just the ratio of marginal densities. And in the case of the null, there's only one density. It's just when theta is theta 0. And then the marginal density under the alternative does involve this G. Now, G, if we had to choose it, that's where a lot of controversy comes in about non-uniqueness and how are you going to justify that. But we don't have to choose it, really, because we're going to get rid of it through the bounding argument. And this is beautifully done in these papers, and one of them is the American Statistician paper in 2001. Good reading there. So the idea is you think of your p-value, which again could come from any kind of complicated modeling context. Then you have this observed, you think of that as your observed data. And under the null, p-values have this uniform distribution. And if the alternative is true, we expect smaller p-values. So they model the p-value under alternative as having a beta distribution, and with the second shape parameter set equal to 1. What that does is it gives you beta densities that are concentrated towards the 0 origin, which is the small kind of p-values. So then what we amount to testing is A equal to 1? Because if A is equal to 1, then our p is uniform, and that's kind of corresponding to the null. And if A isn't 1, then it's not. So the way this Bayes factor is calculated in this setting is you take the marginal densities. Under the case of H0, it's just 1 because that's the density of a uniform. And then in the case of the alternative, we have to integrate the beta density right here with respect to this prior. But instead of actually plugging in a prior, we're just going to maximize the beta density over A, and then it can slip outside the integral, and you wind up integrating G of A dA, and you get 1 for that. So this is how you get the bound. It's that simple. And then this is just a little calculus problem to show that the maximum of this over A is equal to that. And there you have it. That's the Bayes factor bound. So this part of the inequality is just law of total probability and Bayes rule. And then we get this neat little bound for the Bayes factor, and that's why this turns into a bound for this posterior probability of the null. And again, that's probably what researchers want to really know instead of a p-value. So the idea here is, okay, let's keep the p-value, but report also this posterior probability, have that discussion with your colleagues so they know the difference and can react accordingly. And it also is one of those arguments that, as I presented here, suggests that maybe the p-value threshold itself is probably too high if you're going to continue to think about 0.05 as your threshold, probably a bit too high. Yeah. All right. So moving on to the next paper. This one is about aligning p-values with Bayes factors a little bit more on this subject, and part of this will look a little bit familiar. But now the context is different. I got to say this, that when you get these bounds for Bayes factors and bounds for probability of H0 given the data, there's multiple ways to do it, and they usually are within a certain kind of context. Like for example, the previous bound that I showed you was in the context of a point null versus theta equals theta 0 versus theta not equal to theta 0, and that applies to a lot of situations. But you can also add more to the context and get a different kind of bound. And in this situation, we're going to do a one-sided test, and we're going to add normal. So I'm not trying to present these papers in the complete generality that they discuss. I'm just trying to present something that takes a few minutes to discuss and makes you want to go read the paper and see, okay, can I generalize this in a variety of ways? And I think often you'll see that you can. But let's just illustrate that the idea with this context, where we have normal data and a constrained parameter space. So we want to know if theta is 0 or positive. And we can go ahead and let's assume sigma is known to make this simple and easy to explain. That the p-value then calculates to be this. Okay, so that's our p-value. And then our Bayes factor, again, would be the marginal densities under the null. Null is 0, so you just put in 0. And under the alternative, we have to have this prior G, but we're going to get rid of that again. So we don't actually have to choose it. And we're going to do the same trick. We're just going to maximize this likelihood function and basically put in the MLE for theta and slip it outside the integral. You get rid of G and you get a bound. And theta hat is given here. So now it's just algebra to calculate the ratio of these, putting in 0 and putting in theta hat. And you get another bound now that's different from minus p log p, which is what we got in the previous one. Now you get a different bound because this is in a different context, right? You have normal data and you have a one-sided hypothesis test. So it's another way to get a bound. And this was, as I mentioned earlier on, some of the papers in the special issue refer back to other papers that they're highlighting and emphasizing, and this is an idea that goes back a little ways. But it's very useful in the following way, because now we have this lower bound on the Bayes factor as a function. Did you see that? It's a function, it's the lower bound on the Bayes factor, again, it's a function of the p-value only. And you could plot it as a function of the p-value. So this is that bound, and I'll explain the coloring here in a moment. But the bound, I could say now, if I get 0.05 as my p-value, I read up to this bound, and here in the table, it shows you it's 0.259. Why is this yellow? Because if the Bayes factor is in that region of 0.259, then Jeffrey's evidence that, he has the table of if the Bayes factor is this or this or this, here's how you can interpret it. So in this region of yellow, it's interpreted as substantial evidence against H0. But 0.259, and that's at best, right? Here's why it's at best, because this is a bound. We know that BF01 is greater than or equal to 0.259. So if it's greater, then it's actually favoring H0 more. So to take the lower bound on the Bayes factor is like, at best, that's what you could say is there's substantial evidence against H0. And that leads to a lower bound on the probability of H0 given X to be 0.205. So that's kind of consistent that a p-value of 0.05 before we saw this lower bound was 0.289 using the other method. Now it's 0.205, still pretty high, really. And then if you move down to 0.005 on this plot, it aligns with 0.036 as the Bayes factor. And then Jeffrey's rules of evidence say it's very strong. So this is another way to kind of look at what p-values say compared to what Bayes factors say, and try to get some consistency maybe between what the rules for evidence are from a Bayes factor perspective and what the corresponding kind of p-value would be. So, I have in my little tabs here what I'm trying to address, and these last couple of papers that I've talked about are trying to address this idea of is 0.05 a good threshold, or should it be smaller? And then besides that, just kind of supplementing your p-value with this lower bound on the probability of H0. Yeah, okay, all right. Second generation p-values, that sounds like an interesting title, right? We're going to move forward now into the next generation of p-values and calculate it in a different way. And the main point in this paper is that we want to maybe try to get away from these point nulls and think about interval nulls. Now, I think what you're going to appreciate when you look at the special issue is that these papers don't always reinforce each other. They are presenting different ideas. Like, for example, in the last couple of papers I talked about, we saw point nulls, and we dealt with the point null in a different way. Now we're going to look in this paper and say, maybe we shouldn't really be looking at point nulls, but look at interval nulls. This diversity in approaches is healthy, I think, because a lot of the themes in the special issue, if you read the editorial, is to try and be open to context, and context matters. So I don't think you have to say, I'm never going to do another point null again. and I'm always going to do interval nulls. Actually, that might not be a bad idea, but I don't think that's the intent, because, you know, as I said, we still probably want to test if a slope is 0. I don't know. And if we do, though, maybe we can just kind of report and supplement the p-value for that the way that that previous paper said to with that bound. So I just wanted to point out that when you look at the journal, you'll see lots of variety in the approaches that are being suggested. And that's really where the beef is, right? That's where it gives you all of the option and flexibility to do things differently and change the way we analyze data. So, but I do kind of like this idea of interval null, and the descriptive statistic that they're going to propose for a second generation p-value is one that actually conveys whether the interval null hypothesis is supported or not by the data. And it retains the characteristics of a traditional p-value or first generation p-value that is between 0 and 1. Here's a quick look at how it might work. So the idea with this null hypothesis is it's an interval now from A to B. And we're going to go ahead and compute a usual sort of confidence interval based on the data for theta. And we're going to look at how much overlap the two intervals have. So let's just look at this picture here. The null hypothesis in this example, A to B, is the yellow region. So A is 14 and B is 18. That's what our null hypothesis is. And that might make a lot of sense if you feel like any number between 14 and 18 is really the same in terms of the practical impact it has. That's the whole idea of a null, interval null, is that, you know, it isn't just one value that has all the importance and interest. It's a range of values that if they were 14, 15, 16, 17, it doesn't matter, right? It has the same impact on real life. So you compute this confidence interval, and that's the black line. So I have 4 cases here. In the first case, the confidence interval is completely within the null. And therefore, there's complete overlap, and the second generation p-value is 1. And that's really, of course, that would intuitively suggest strongly that the null is probably true, right? If your confidence interval is completely within the null interval there. But let's skip down to this case. Here's where the confidence interval is completely outside, no overlap. That would be the case where p is 0. And then a couple of cases in between, like here's one where what we're measuring is how much overlap does the null interval have with the confidence interval. And here it's a 4th, because this amount here is 1/4 the total of the confidence interval. So here again, this is a very simple thing to compute. And they look at it pretty carefully. And one of the things they show that's of interest is that if the null is true, then the probability that you get a 0 p-value is less than or equal to alpha. So it does retain sort of a frequentist property that you would want to have, that, you know, if from a p-value point of view, that if H0 is true, you're not going to be getting this kind of situation. It's less than or equal to alpha is the probability you'd be getting that. So another paper in the special issue also argues the case to focus on interval nulls. They do it a little bit differently. They say, okay, let's reject the hypothesis, the null, only if there's no overlap, and let's see, reject only if there's no overlap between the interval null and the 95% confidence interval. So as long as there's no overlap, go ahead and reject. That's the rejection rule. But they look at other options, including this one, where they'll say reject if the p-value is smaller than 0.05, and also the observed effect size is greater than a minimum effect size. So they're trying to combine different things that you would like to see as evidence against the null before you actually decide to reject. So this is kind of along the lines of that supplement of goal. But so as I was thinking about this paper and the previous one, it occurred to me that we do have methods that are quite general that apply to interval nulls. So I just wanted to make this comment about union intersection tests, because they are a very flexible tool we have already to handle hypotheses of this type. You know, this hypothesis is the intersection of two one-sided hypotheses. And because it is, we can test that by rejecting, using the union of two rejection regions that are based on the one-sided hypotheses. And that will work for a lot of situations. And even in this particular setting of normal data, there's a UMPU, Uniformly Most Powerful Unbiased Test, published in this American Statistician Journal, 1996, a very nice description of this really interesting test that you can show is to reject when this is greater than C and C solves this equation. Look at the power function of these three tests actually. So this is going to highlight one of the concerns that we know about for sharp nulls, because the blue line in this graph is the power of testing if mu is 2.5 versus not 2.5. There's your sharp null, right? And the blue line shows, of course, when mu is 2.5, you get your alpha power. And then it grows nicely as you move away from 2.5. But in a way, it grows too nicely. Because look what happens when it's 200. It's very steep and very high power, right? And so even if the mu is 2.52, you'll probably reject, right? This is what we kind of regret about simple sharp nulls. But now instead, if we do this union intersection test, this is the black line, we see the desirable behavior that anytime we're in this region 2 to 3, we're not rejecting. And we shouldn't, if we think that values between 2 and 3 are all reasonable and we feel indifferent about them. And then we only reject when we're outside that interval. And it maintains that shape as we increase our sample size. Whereas the blue curve, you know, it gets more spiked. And the red line on here is just the UMPU test, which has a bit more power. It's kind of interesting to see how the union intersection test is quite a good rival to the optimal test here. Okay, so I wanted to conclude with a discussion about one more paper, which is going to now try to reconcile the frequentist approach to the problem and a Bayesian approach to the problem. And this kind of addresses the holistic approach to data analysis, you know, or instead of method diversity. One of the papers in the special issue called it method diversity. I don't remember which one, but I like that concept too. So in this approach, let's suppose that a data set is analyzed by a frequentist, or I think better, by you wearing your frequentist hat first, and then we'll put on our Bayesian hat in a minute. So we're going to do the frequentist analysis first. And then when we put on our Bayesian hat, we'll say, what are the priors that I could assume, because this is the challenge right now, what to choose for these priors. What are the priors that would support that outcome from the frequentist analysis? And then do I believe those priors could be feasible for my problem? Or from my holistic view of this problem, do I have reason to say that not all those priors are feasible? You know, I'm going to use more information than just the data that I have, that I feel confident in. This is bringing in, right? This is definitely an alternative, right? I'm just not going to just stop with the data, but I'm going to think about what else I have that I could bring into the problem, and then would I dispute the finding that I got from not doing that? So here's an example. Suppose that we are in this, again, these are just like the baby examples that illustrate the idea simply. I'm not saying that in this particular case that this would be easy to do in the most complex problem you can imagine. You know, probably could be more difficult. But we don't always work on those types of problems. Sometimes we have problems that are like this, right? And then if you have more of those complex problems, you might have to, you know, to actually try and make this procedure work. It's kind of, I should say, it's kind of like reverse engineering is what we're doing. We're going to reverse engineer a Bayes analysis by looking at what priors I would need to have, and then do I think that that's reasonable? So you can imagine in very, very complex high parameter kind of models. This might not be easy to do, but fortunately, not every problem we ever work on is that hard. So that again says that you can pick your tools for the context that you're in and not always use the same approach. I don't think there's anything wrong with varying it up a little bit depending on your context. So in this illustrative example, we have, I'm going to take the variance to be known. Let's go ahead, do the frequentist analysis, and I get my confidence interval between L and U for the parameter mu. And suppose now 0 isn't in there. So now the frequentist analysis would say, okay, there's a non-zero effect. Yeah, because 0 is not in there. Now, suppose you put your Bayesian hat on now, and you're going to be skeptical. You're going to say, I really, my other information, I'm not sure that it really tells me that there's an effect. So let's put a prior around 0 with a to be determined variance, phi 0. Remember in the slide here, phi is the variance of the data, which I'm taking to be known. Now, phi 0 is my variance of the prior. So the math for this results in a 95% credibility interval that's equal to this. Okay, so we have this confidence interval, 95% confidence interval, LU, that's the frequentist answer. Now we have this 95% credibility interval from the Bayesian analysis as a function of phi 0, which is not specified yet. But what we're interested in is when do these two intervals agree? And you can do the math on this algebra, that the credibility interval, this one, will exclude 0 also, because remember the premise here is that the frequentist interval, the premise here is the frequentist interval is not in 0, right, I'm sorry. 0 is not in L to U. So the premise is that the confidence interval for the frequentist does not include 0. And that will be the case for the credibility interval. It'll exclude 0 also, but only if the variance in your prior is greater than this. And this is interesting, look at that. It depends on U and L, right? So I have U and L from the confidence interval. And this is not a typo, that's the 4th power. Yeah, so it's a little bit interesting formula, but it's easy to calculate. And so you can just plug in L and U there and you get phi 0. So now the skeptical Bayesian could say, well, it's going to exclude 0 if phi 0 is greater than that, but I have other information in a holistic view of the problem that tells me that I don't need to make phi 0 that big. I have good enough prior information on mu that I can make phi 0 smaller. And then if I feel that way, I would dispute the frequentist finding. What is that? I'm disputing myself if I'm doing this myself, right? But that's an important thing to be willing to do, is question yourself, right? Because yeah, maybe I'd like to do the confidence interval, but if I then did this and I got a different answer because, yeah, that made me think I do have other information. I don't think it's reasonable that the prior variance should be that big, So I'm going to go not so fast, declaring significant, and think more about this problem. And I like that. I like that idea of being able to say, to have consistent results between the frequentist and the Bayesian analysis, I need to have enough information to say that the variance of my prior needs to be smaller than some number. Yeah. And finally, just to say that this goes the other way too. If 0 is in the confidence interval, now the frequentist would say there's an effect, no effect, would say there's no effect. So now you put the Bayesian hat on, but now you're an advocating Bayesian because you think, well, let's just play sort of like the devil's advocate. And I'll say that, I'm going to put a prior for mu on some non-zero mean, but I have 2 parameters here now. I don't want that, and I don't need that because I can put this constraint on the problem that says, okay, my prior is such that it doesn't have 0 as the mean, but it allows a 5% chance of less than or equal to 0 values, which would be consistent with no effect, right? So you just turn this into a single parameter unknown with this constraint here. And then you say, now the credibility interval is going to include 0 and agree with the frequentist if and only if phi 0 is greater than this. Another interesting looking formula. But the math is just algebra to get that. And it depends on U and L the same way as the other one did. And again, now you can say, well, you know, if I had information that the variance in my prior could legitimately be less than that number, then I would dispute that finding too. And if I don't, then I have consistent outcome, and there's no ambiguity or reason for having the need to look at things more carefully. But when you get opposite conclusions from the frequentist and the Bayesian analysis, you haven't really reconciled. That's why I called this tab reconcile. You haven't really reconciled the two approaches, and it should prompt you to be more contemplative about really what to conclude. All right. So I think that's the end. And I hope if I've achieved what I wanted to achieve, it would have been to encourage you to go to the special issue and read more about all that I just talked about and the other papers that are in there.
Thank you, Dan, for that very informative talk on the alternative methods. We have received some questions from our attendees. And one of the questions is, in large-scale inference problems like GWAS studies, the genome-wide association studies, the complete null is absolutely impossible. Ranking and effect sizes are more of primary interest. Will you agree to abandon the p-values in such cases and maybe use one of these alternatives? If not, what will you see the merit of using the p-value in these cases?
Well, I think the merit of the p-value is in that it leads to a bound on this probability of H0 given the data. So you still need the p-value to compute these bounds. I don't think I would abandon the p-value. Mm-hmm. And I would probably, the paper by Benjamin and Berger that gave you that simple kind of bound to compute as a supplement to the p-value is what I would use.
Thank you. And one more question, I think we have time for it. This question is from Yu Du, and Yu states that in some cases we have to make a binary decision, like drug approval, to approve or not to approve. It is not on a continuous scope in these kind of situations. So it seems in this case, whatever alternative to p-value less than 0.05 would also cause some similar problems. Do you agree with that, or do you think maybe some of the alternatives would not cause some problems?
I think if you just change the threshold, you're right, that there's still going to be a bright line threshold that you're above or you're below. It might be that you have less risk for false positive if you lower it. But I don't think that's really the spirit of some of these alternatives to by itself change the threshold, but to also supplement the p-value that you're using with some sort of follow-up analysis, either the bound for the probability that H0 is true, which is really what most researchers want to know, or trying to do this sort of reconciliation between the frequentist analysis and the Bayesian analysis, as that last paper showed. So I think these alternatives are deeper than just lowering the threshold and saying that's going to solve all the problems. No, I think you either want to supplement or do something more holistically.
Exactly. Thank you so much, Dan.
Okay.
And I would like to move to our last speaker, Dr. Jessica Utz, who is Professor Emerita in the Department of Statistics at University of California, Irvine, and was the 2016 president of the ASA. She served as chair of the UCI Statistics Department for 5 years and led the department in initiating a major in data science. Her honors include being an elected fellow of the ASA, the Institute of Mathematical Statistics, the American Association for the Advancement of Science, and the Association for Psychological Science. She's the recipient of the ASA Founders Award, the IMS Harry Carver Medal, the Distinguished Service Award for the NISS, and 2 awards for distinguished teaching. She has served as the president of the Western North American region of the International Biometric Society, chair of the Committee of Presidents of Statistical Societies, and is currently on the Council of the International Statistical Institute. She has a long-standing interest in promoting statistical literacy and has published 3 statistics textbooks with that emphasis. In addition to statistics education, her research involves applications of statistics to a variety of areas, most notably parapsychology, for which she has appeared on TV shows, including Larry King Live, Nightline, and CNN News. And today, Jessica will talk about, in light of these alternative ideas, how we might teach and influence our interdisciplinary collaborations. Jessica?
Okay, thank you. Thank you, Ezra, and thank you for inviting me. So this is what I was asked to talk about, and I'm mainly going to focus on papers in the special issue that address these issues, but also give a lot of my own ideas. So as you know, there are many ideas in the editorial, the lead-in editorial to the special issue of the American Statistician, but I'm mainly going to focus on the most important recommendation, which is eliminating the use of statistical significance as defined by a concrete rule. And my focus is going to be on what we can do to help implement the recommendation by working with these various groups, our statistical colleagues, our non-statistical colleagues, journal editors and reviewers, students, including graduate and undergraduate in statistics and other, and teachers of introductory statistics. I'm just briefly going to think about textbook authors. I am a textbook author, as Ezra mentioned, and I'm just starting a new edition, so I'm struggling with this myself, how to deal with this problem. I am assuming that most of you who are listening are statisticians, or at least are the statistical help for people in other disciplines. And if some of you are not, that's great too, because you can get a head start on what you should do with your statistical colleagues. So here's the recommendation I'm focusing on, and I'm going to read it here. I'm assuming most of you read it, but just to be sure we're on the same page. The ASA statement on p-values and statistical significance stopped just short of recommending that declarations of statistical significance be abandoned. We take that step here. We conclude, based on our review of the articles in this special issue and the broader literature, that it is time to stop using the term statistically significant entirely, nor should variants such as statistically different, p less than 0.05, and non-significant survive, whether expressed in words, by asterisks in a table, or in some other way. And there's lots of support for this statement, and there has been for a long time. This is one that I found the most sobering, and this was in the special issue that was published on the p-value statement back a few years ago. This is by Ken Rothman. Scientists have embraced and even avidly pursued meaningless differences solely because they are statistically significant, and have ignored important effects because they failed to pass the screen of statistical significance. It is a safe bet that people have suffered or died because scientists and editors, regulators, journalists, and others have used significance tests to interpret results and have consequently failed to identify the most beneficial courses of action. And one thing that I find convincing, especially to non-statisticians, because I think statisticians already essentially know this kind of thing, is what's called the hypothesis testing paradox that was shown to me by Bob Rosenthal. Some of you may know Bob was pushing this kind of thinking long ago. He was the one that first published the idea of the file drawer way back in 1979, and is one of the pioneers for meta-analysis. So here's the paradox. A researcher conducts a test with a sample size of 100 and gets these results: a t-statistic of 2.5, a p-value of 0.014. The researcher is very happy because they get to reject the null hypothesis. But just to be sure, the researcher decides to repeat the experiment. But because the initial result was so obvious and strong, the researcher decides, I don't need to go to all the trouble of getting 100. I'll just use 25 this time. And of course, you know what's going to happen. The result now shows a t-statistic of only 1.25, p-value of 0.22, and the researcher cannot reject the null hypothesis. And so for somebody who's not statistically savvy, it looks like the effect has disappeared. So the researcher decides to try to salvage things by combining the data. So now there's 125, and now, lo and behold, the t comes out to 2.795, p-value is 0.006, and the effect seems even stronger than it was the first time. So here's the paradox. The second study alone did not replicate the finding, but it was combined with the first study, and that made the effect seem even stronger than the first study. So the point here is that if we define replication by getting statistical significance each time, or even on the basis of getting a similar p-value, That makes absolutely no sense. And yet, it's very common practice in many disciplines. And of course, what's going on here is that in all three cases, the effect size was the same, 0.25, but the test statistic and the p-value change based on the sample size. And in fact, t is just equal to the square root of n times the effect size. So all three cases had an effect size of 0.25, but you can see the effect of the sample size on the test statistic and the p-value. So I find that this is somewhat convincing to people who are not statistically savvy because they are used to thinking just in terms of statistical significance, and this points out how silly that is. So I want to be clear. I think both Nicole and Dan were clear on this as well, but we're not advocating getting rid of p-values. We are advocating a better understanding and a more thoughtful interpretation of what they represent. And we're also advocating the elimination of the dichotomy of statistical significance, whether it's a 0.05 or some other value. One of the papers in the special issue noted that the better approach would be to accept uncertainty and embrace variation in effects. We can learn much, indeed more, about the world by forsaking the false promise of certainty offered by dichotomous declarations of truth or falsity, binary statements about there being an effect or no effect based on some p-value or other statistical threshold being obtained. So why is it so hard to make the change? Like I said, people have been talking about this for a very long time. And I like this quote from Steve Goodman in the special issue. And basically he says, the basic explanation is neither philosophical nor scientific, but sociological. Everyone uses them. It's the same reason we can use money. When everyone believes in something's value, we can use it for real things. Money for food and p-values for knowledge claims, publication, funding, and promotion. It does not matter if the p-value does not mean what people think it means. It becomes valuable because of what it buys. Okay. So how do we remove the high status of statistical significance as the coin of the realm? That's what I want to talk about. Well, I think we need to start with ourselves as statisticians. And so my first recommendation is that if you haven't done so already, get a discussion going with the other statisticians that you work with in your department, your school, or your workplace. And base the discussion on the papers that are in the special issue of the American Statistician, especially the editorial, and focus on understanding the big picture problem. Because I think, as you can see from Dan, there are a lot of suggestions for what to do about it. But I think the first thing is that everybody needs to agree that there actually is a problem that needs to be solved. Okay. And for colleagues who are not statisticians, I think we need to realize that there is no one-size-fits-all replacement for the current obsession with statistical significance. So scientists and statisticians who are working in a particular discipline really need to decide what's best for that discipline. And I think some of the issues to consider are whether the research is mostly cumulative or are studies unique. For example, if you're working for a water resources board and you need to decide whether or not a pollutant is a problem in a certain area, that's a unique study. That's not building on other research that's been done before. Whereas if you're working in something like whether, let's say, whether active learning helps students learn better, then that's cumulative. There's been research and you want to build on what's done before. So those are different kinds of situations. You need to consider if there's expert knowledge that could be incorporated using Bayesian methods. You need to decide if the main goal of the research is to make decisions, or is it more focused on increasing understanding? And then I think you need to decide, would it be more serious to miss an important finding or to think something's a problem or a solution or a difference when it's actually not? So those are the kinds of questions that really should determine what kind of replacement to use in particular disciplines. So my second recommendation, if you work with scientists in other disciplines, start a discussion based on the TAS editorial and issues like the ones on the previous slide. So ask your collaborators to read the editorial and discuss it with you. Find and disseminate papers in the discipline that demonstrate sound statistical thinking, but that don't rely on statistical significance, and use those as best practice examples. I encourage you to give talks at disciplinary conferences on this problem, write an editorial for a journal in the discipline, and contact editors of journals. And I'm going to show you two examples of people who are doing that. The first one is for nursing journals, and this is new on May 6th of this year, statistician Matt Hyatt and 24 co-signers who all collaborate with nursing researchers and educators sent a letter to the editors of 18 nursing journals requesting changes in their author submission and publication guidelines. And I'll show you what they were requesting on the next slide. They also offered to meet with the editorial boards to discuss. And the results so far, and remember they just started this on May 6th, are that already 5 of the journals have agreed to do this. One more is in the process of working it out, and one has even asked for an extended article to publish on the topic. And then many more of them are considering the suggestions. So I consider that pretty good progress since they just started this effort. The core recommendations in the letter to the journals, and this is a direct quote, specifically in line with the recent efforts by the ASA, we recommend including the following manuscript submission requirements. 1, when a p-value is reported, state its value, regardless of how small or large it may be. 2, avoid using 0.05 or any other cutoff for a p-value as the basis for a decision about the meaningfulness or importance of an effect. And 3, in reporting a p-value, a measure of the effect size should be included along with a corresponding interval estimate, for example, confidence interval. So 3 simple suggestions. The second example is from the paper that I actually co-authored in the special issue. And Stuart Hurlburt has been very active in trying to get journal editors to sign on to this. So he has sent a letter to over 200 journal editors and grouped them by society in the same email so that he would encourage discussion among the editors of the various journals for that society. And the start of the letter is, we write to present a modest proposal for your consideration that in the instructions to authors for journals under your editorial care, it be stated that authors should refrain from use of the phrase statistically significant. Very simple request. The full letter was 2 pages. And it gave references to the special issue and other resources and additional justification. And so far, a dozen of the recipients have responded that they have our recommendations under discussion by their editors and editorial boards, and 4 have invited us to submit an op-ed or a commentary or an editorial to their journal. Now, what about education? Let's move on to that. There were a couple of nice papers in the special issue that discussed in particular what to do about education. One of them was by a group from University of Washington and other places, but about a course that's taught at University of Washington. And the paper was titled Beyond Calculations, a Course in Statistical Thinking. And I want to point out that this course that they're describing is intended not for a general education course for students who don't take any other statistics, but rather for senior statistics majors. And here are some quotes from their paper about why they're doing this or what they're doing. There's a pressing need to move statistical analysis and evidence-based decision-making beyond the current system of over-testing and under-thinking. Our course is intended as a bridging course. It serves as a bridge between statistical knowledge and successful application of statistics in science. And then finally, formally and informally, teaching statistical thinking is perhaps our biggest, best, and easiest opportunity to make a positive impact. Here's a second example. This was a paper by a group from Miami University of Ohio. And what they did is put together a way to audit what you're currently doing. So here again, quoting, for a department to perform a comprehensive audit of p-value concepts in their introductory statistics courses, we propose a framework that elicits both intra-departmental and interdepartmental feedback on the current curriculum. And in their paper, they provide a rubric for evaluating your current introductory stat courses. They provide a framework for focus group discussions with colleagues from across campus, and they provide resources for others who want to improve understanding p-value principles in their courses. So my recommendation number 3 is to help change undergraduate and graduate education. So investigate the current offerings on your campus to determine whether they cover understanding basic principles, and you can use the audit presented by the Miami University people. Consider offering a statistical thinking course for statistics majors. Convene a weekly discussion with your statistics graduate students to work through the TAS editorial and some of the papers. You need to make sure that none of your statistics graduate students leave without understanding these ideas. And then finally, offer to give seminars to graduate students across campus to discuss the ASA p-value statement and the TAS editorial. I happened to be ASA president when the p-value statement came out, and I gave a lot of talks on it, and they always generated big audiences. And then finally, I want to end up with this quote from Lily Tomlin. I always wondered why somebody didn't do something about that. And then I realized that I am somebody. So my recommendation number 4 is, at least if you agree with these with the recommendations in the editorial, do something. Just get started and do something. Okay, and you can see that since 1988, I have been advocating that we not use p less than or equal to 0.05 as the criterion for making decisions.
Thank you, Jessica, for all the information, especially the recommendations. We have received a question about how to change the current teaching paradigm, which I think you did briefly address. But one thing that I think we are all thinking about is, as individuals, as professors, what can we do in our classes right now? For instance, especially when we're teaching to seniors who has learned this p-value since the beginning of their undergraduates, what do you think, how can we, what could be our initial steps? How can we start inserting this information?
I think the most important thing is not to get rid of the idea of p-values, but to get rid of the idea of statistical significance as the hard and fast bright line rule. And I think others have talked about that. And I think the best way to do that is to help students understand what's wrong with just using statistical significance. I also think we need to still discuss it because obviously it's out there in the literature and it's going to be for a while. So students do need to understand what statistical significance means, but they also need to understand the problems with using it as the sole criterion. And so I think, for example, that hypothesis testing paradox that I showed is one very simple way to illustrate the problem with we're using statistical significance alone as a criterion, but just getting people to understand what the problems are, what the issues are.
Thank you so much. And with that, I would like to open the floor for a general discussion. We have received some questions for all our speakers. So I would like to ask some of these questions to all of our speakers. And one of them is coming from Ligong Chen, and Ligong states that, as we have also pointed out, I think that we need to clarify what the statistical significance means. Ligong's example is that in the t-test, there are 2 sample means, x bar 1 and x bar 2, and we can see the difference between these 2 sample means. Since the difference is composed of systematic error and random error, how can we make a judgment on these 2 kinds of error? And Ligong states that we definitely have no way to measure the true magnitude of either systematic error or random error. What do you guys think of this? Is that would one of the alternatives might be able to address these 2 types of errors we have in terms of t-test? And then if we're going to abandon maybe p-values or start using these alternatives, how can we end our research conclusions? If we're going to just, should we end them with just saying this is the difference? How can we further this? What will be our inferential procedures then? I guess that will be the highlight of his question. If anyone wants to start with that.
Okay, I'm a strong advocate of estimation, whether it's for using confidence intervals or effect sizes. I think it depends on the purpose, but I'm a strong advocate of simply replacing the whole idea of significance testing with estimation, because you can see 2 things. You can see whether you have a strong effect or a weak effect, and you can see how much certainty or uncertainty there is about it. So that would be my first pass.
I was just going to comment, I'm a little unsure about what's meant by systematic error. I get the random error part, and then normally I would have anticipated having a systematic trend or effect that was supplementary to that. So if it's a different kind of random error, it seems like it's a different kind of model than what a t-test would be used for.
Right. Yes. Thank you for your responses. And a lot of our actually questions were surrounding on a good design. So basically our attendees were asking whether a good design of a scientific study and good data quality, are they more important than lowering or abandoning the p-value or using some other method? Some researchers in these cases, if we start using the alternatives, maybe some researchers may be interested in finding out ways to reach the statistical significance also with these alternative methods, which might also lead some kind of p-hacking. What are your opinions about this?
Well, I'll take a first stab. Others obviously jump in. So, I mean, I think we touched on this a little bit already. You know, if you have a bright line threshold that is going to determine which results you pay attention to and which ones you don't, then that's going to lead potentially to these types of behaviors, which is why I, at least, and I think not only I, but others as well, think that we should not abandon the p-value, but abandon this bright line threshold cutoff. That's, I think, more of a problem than the p-value itself. I think if you have a good study design and you have good quality data, then that is obviously worth a lot, and getting that is not easy. So that's why, you know, we advocate as well being thoughtful and sort of thinking really about what you're doing and why you're doing it, and not just sort of blindly applying some method that you were taught in grad school or whatever.
I don't think the alternatives are going to be bulletproof to nefarious kind of activities, but I think they encourage more transparency in what the thoughts behind making different assumptions are. Just for example, the bound that I was talking about requires choice of pi 0, which is the probability of your a priori probability that your slope is 0, say. You could play games with that, I suppose, but it's right in front of everyone to see what you're assuming for pi 0. So it would probably be more of an open kind of analysis that would be subject to vetting a little bit more carefully than some of, you know, a lot of the ways p-hacking might happen now is you choose the wrong model to make your inference that doesn't really fit, but it gives you a small p-value. And sometimes that could be hidden perhaps more easily because the model itself is kind of way behind in the background to the calculation. So I think at some point ethics comes into this, right? We have to rely on good teaching of ethics and principles, and but I think the idea with the editorial associated with the special issue was to encourage openness and transparency and humility and modesty. All these attributes are really part of just having a good set of ethical principles.
I'd like to add a little something. I think one of the things that came out of the original p-value statement that ASA put out was the idea that the focus has always been on the null hypothesis as the thing that might be wrong when you reject the null hypothesis, right? But there's all kinds of other assumptions built in there, and the model is one of them. And a good design is really important there. So there could be things going on behind the scenes if you don't have a good design that leads you to reject the null hypothesis under the old framework, where it's not really the null value that's the problem, it's the way you design the experiment. And I agree with Dan that I think the ethics and of good design and where we get data is becoming increasingly important as more non-statisticians are getting involved with data science and analyzing data. I think that's something that statisticians really need to be at the table to contribute, is the whole idea of how the study was designed, where the data came from, and whether or not the purposes for which it's being used are appropriate given the way the data was collected or where it came from.
I'd like to add just one more thing. I don't know if everyone is aware, but there's also a movement for pre-registering your studies. So you can put it out there. This is how I'm going to collect my data. These are my hypotheses. This is how I'm going to analyze the data. And there are even journals that are starting to take the stance that they will accept or not your paper before you've done anything based on the soundness of the science and the soundness of the analysis. And that relieves the pressure of having to get to that significant 0.05 or whatever other threshold level, because you'll just analyze your data the way that you said you were going to analyze your data, and whatever comes out, comes out. So that's another protection that's starting to come into play.
Thank you. And one other question, we have a few questions again related to how we design and determine the sample size in light of all these ideas. One question is, in the planning stage, it's common to estimate sample size based on the statistical inference and type 1 error rate of 5%. So do you recommend that we should also rethink how we plan on the sample size based on all these information that you have presented? Should it also affect how we design, how we think of our designs?
Well, I think that should always have been the case. I think the focus on, you know, am I going to get such and such power at 0.05 has been misguided to begin with, and that you should think it through more clearly, like what magnitude of effect is really going to matter and how certain you need to be so that you're getting that magnitude. So I think, yeah, we need to rethink. A little more thought needs to go into that.
I wanted to say something that I think is pretty funny, and it's not I heard this somewhere, I don't remember who, but a very simple sample size formula that doesn't involve alpha and beta is N equals budget divided by cost per sample. So now kidding aside, I think really with sample size calculations, which are very intricate actually, to be able to understand all the sample size formulas that exist requires a great deal of knowledge about so many different types of models and analyses. But and sensitivity studies are always the way to present options. And then, yeah, budget does come in. So it isn't just going to be alpha and beta, but you have to have some guidance to what could your money buy you.
Exactly. Thank you for that answer. We have actually a lot of questions. I'm trying to ask most of them. We have one question from Hal Switney, who's asking why abandon the phrase statistical significance. That phrase, implying p less than 0.05, has been defined to allow too many false positives. And I think we do agree with that to some extent. Many, if not most, consumers of inferential statistics need to make dichotomous decisions, such as we talked before, approve a drug or not, approve a loan or not. And the better approach, he suggests, is to make alpha a decreasing function of sample size n, which would decrease false positives and p-hacking. What do you guys think about that? If anyone wants to jump in.
I think there is a paper in the special issue that does that very thing. I remember the author is Rebecca Batensky, I think, that gives a mapping of alpha to sample size. I believe that's the author. If I'm wrong about that, I'm not wrong that the special issue definitely has a paper that covers that perspective.
Thank you, Dan. Another question we have from Daniel Cohen is, can any one of you address using p-values to do model fitting? So what methods are available to decide if predictors or interactions are relevant? I guess maybe some of the methods you suggested, Dan, would also be used to address this question. How can we use p-values or alternatives to the p-values to the model fitting?
Yeah, I mean, regression, model fitting in a regression context is testing if slopes are zero. So, because usually if you don't reject the null hypothesis, you kind of drop the term from the model, right? So before you just use the p-value, you might use these bounds on the probability of H0 given the data to decide, should I drop it really? If the p-value is 0.048, but the probability of H0 given the data is 0.27, do I feel comfortable dropping that from the model? Maybe not.
Right.
There's also some interesting work being done now on what's called, I think usually called post-selection inference or something like that. So this is work, Benjamini has done some work on this, and Rob Cipriani has done some work on this. So how you, but if you look at the p-values that come out of our typical model selection procedures, they're actually, they're deflated, I believe, so that things look more significant, quote unquote, than they actually are. But if you properly account for the very complicated things that you're doing when you're fitting a model, there's a lot more going on there than we're even really typically aware of. So, you know, I'm going to be teaching a regression class in the fall, and I'm already thinking about how I'm going to modify what I tell my students in light of all of this, and how I get them to a point to be thinking about the model selection process in a more principled way. I think it's a really hard question, but it's very interesting.
Yeah, and I agree. It's actually a difficult question to teach as well. I think how we're going to teach in light of these alternative ideas is also a big question, which Jessica has pointed out in her recommendations. A couple of questions about how do we go to reporting at this stage? Because I think one of the messages that we're giving is being transparent. Instead of using a cutoff value, report the p-values and effect sizes. One of the questions we received is, if reporting the p-value, what will be your recommendations for preventing the interpretation that large p-values support the hypothesis that there is no effect, rather than indicating inconclusiveness? What do you think should be, should we just leave it there? Should we just report the p-value, which is large, and just leave it like that? What do you think should be, could be done further in that reporting? Is there anything that could be done?
Well, I think it's important when, you know, really, what we're really asking is that people be more thoughtful in how they present their results in papers. And I think in the past, what's happened is that, for example, the results that came up with p less than 0.05 are the ones that go into the abstract, they're the ones that get picked up by the media, and so on. So I think just more thoughtful reporting. And one of my suggestions was to look for best practice examples in disciplines and show people how it can be done. In our paper in the special issue, we have a few examples of papers that don't use statistical significance at all, and yet they can convey the importance, that, what was important and not important in the results of their studies. So looking for papers that have done that as best practice case studies, I think, is important. But just moving away from this idea of yes and no thinking, and reporting the results in a more nuanced way is what we need to train scientists to do.
Yeah, I agree, and I think there are examples that are out there, and finding those and building on them, I think it's really the best way to get people to think about changing their thinking or switching their thinking. Yeah, I won't say more. I agree with Jessica. I think the examples are out there. We just need to find them and highlight them more.
I think I still probably fall into the comfort zone of thinking that large p-values could be a power issue or just a really small effect size. But I want to go back to Rebecca Batensky's paper, because I'm pretty sure that is the one. She actually does talk about how large p-values can provide evidence for the null. So I don't think I can describe all those details here, but if you want to know more about that question, you should really read that paper in the special issue.
Yeah, actually, we received a question about what do you think would be, where can we find these best practices? And I think we will refer them to the open source special issue of the American Statistician to look for the best practices. One question is, again, as I said, we're receiving a lot of questions. I'm trying to ask as many as possible. Do you think decision theoretic approach could serve as an alternative to p-value? In other words, the decision is based on maximizing a utility function or minimizing a loss function, which can take into many factors into account. What do you guys think about that? I think it would require some thinking maybe to decide whether it could be possible, but do you have any initial thoughts?
It certainly promotes the idea of holistic view, because it's bringing into the problem, the consequences of mistakes in terms of some sort of cost or cost ratio. So I think if you have a good foundation for that kind of extra information, then that is the idea of alternatives, to try to use it in some formal way. And I'm starting to sound a little bit like a broken record, but there is a paper in the special issue that does talk about decision theoretic alternatives. So please take a look at that one. I can't quite remember the author, but I guarantee you there's one paper in there.
And okay, I think I will have one more question. I think this is again to you, Dan, about the alternatives. Do you think that one of our attendees is asking, it seems the essence of all the alternatives and the training is that frequentist methods ignore all history and evidence outside the current experiment. And how do we convey and convince frequentist regulators and others how to reduce risk by incorporating other evidence?
Yeah, I don't know if it's quite that cut and dried. I think frequentists incorporate history and evidence in their model formulation.
Mm-hmm.
You know, it's kind of like part of specifying a normal distribution for the data is based on some experience. It's not flying blind. Of course, there's diagnostics to test that as well. So, you know, Bayesian is inference, different kind of incorporating an additional kind of information, but it's not one school of thought does and one doesn't. It's just different types of information, I think.
And I would just add that a Bayesian approach is not a panacea. We could easily run into the same sorts of problems with Bayes factors or with other types of Bayesian analysis as we do with p-values.
So it's kind of like the method diversity, right? It's like not one size doesn't fit all, I think is something in the editorial. And I don't think we have to always be one type of analyst. You know, we can vary it up depending on the context. As it's often been said too, context is everything.
Do you think that's also true when we decide to use which kind of alternative method to use? We need to think about our problem because you have presented a variety of alternative methods. Do you think we should also think about hardly about our context, about which one of those alternatives we should choose?
I do, and because I think you know, first thing is like, should I have a sharp null or an interval null? Does it make some sense to be testing one or the other of those hypotheses? And then depending on what type of information you have, like the last method about reconciliation requires more information about the traditional sort of priors in a Bayesian analysis, whereas some of the bounds discussed in the first part of the set of papers kind of get rid of that piece of information and introduce this bound. So yeah, I don't think that we would think that there's one alternative method there that's going to become the workhorse. I think it's going to be spread out over a variety.
Yes, thank you for that. And one last question. I think this is for Jessica about education. Megan Lutz is asking that we have discussed how the education should be changed for upper level undergraduates and graduate students, but she wants to begin her majors to catch the boat early. How can we do that? What will be the first steps if someone is just starting to learn about statistics?
Okay, hi Megan. If they're going to go on to be a statistics person as opposed to just taking a single course, I still think they should start with a course that focuses on statistical literacy and discusses these various ideas. I think too often our students are trained technically, but they need to learn early on that there are these problems and issues and this history of doing things in a way that might not be the best. And so I think a statistical literacy or thinking course early on for majors is just as important as it is for non-majors, just to get these ideas across.
Yes, thank you. So we're just about to close our webinar. I would like to ask our speakers whether they will have anything else to add before we close our webinar. Any kind of last words?
I just want to say that in preparing to give talk on the papers in the special issue, it was really an exciting time to open up my own mind to being receptive to trying different things with p-values and taking to heart the issues that we need to be aware of when we're teaching about them and talking to our colleagues about them. So I think this special issue, if you spend time with it, could be transformational for you if you're open to kind of digging into the details a little bit and seeing what the other options are. I think it's it's been that way. Nicole mentioned it was that way for her in her experience, and Jessica, I know, with her teaching experience and ideas, and mine from the side of collaborating with interdisciplinary colleagues. I have more to say to them now because of my awareness and study of these papers.
Yes, so thank you, Dan, and thank you, everyone. So we're just about out of time. I need to wrap up this very interesting webinar. I'd like to thank all our speakers for giving us invaluable information and their recommendations on how we should move forward with our research, our teaching, and our collaborations in light of these alternative ideas. I would also like to thank our attendees for joining in and asking questions. Following this meetup, you will be receiving via email a link to a brief survey so you can provide us some feedback and suggestions for future topics. And finally, I hope you will all participate in the upcoming events, and I hope you all have a great day, and thank you all for joining in. Thank you. Bye-bye.